Wonderful. Okay, thanks everyone so much for coming. Welcome to the ELEC2133 Finals Crash Course. In the midterm crash course, we went through a lot of amplifier analysis. So we're not going to be doing as much of that in this section. I was thinking of covering more to do with feedback topologies, and we might be able to have a look at the 2019 past paper as well. So if we have a look at some of the content that you've got to cover, essentially any of this is fair game in the final. So there's op-amps and analog functions. This is going to be things like your sort of summing or difference amplifiers. Other things might be, just different circuits that might be based on operational amplifiers. So it's not just going to be your sort of your classic setup. There might be some different intriguing things happening there. Next is just understanding the operation of diodes, BJTs, and MOSFETs. We didn't really look into diodes in the midterm crash course, so if you're interested in more to do with diodes, then I think there's an interesting question a bit later on. We've also got BJTs and MOSFETs sort of in situ in designs and analysing those, which, as Leon said, was the 12 different Thevenin resistances, all that fun stuff. It does take a while, so we'll see how we go if we get to a question like that. Next is multi-stage linear amplifier circuits. So these are sort of like a differential pair and then the op-amp, like in your labs, or other sorts of setups like that. Sorry, let me zoom in a bit. Must be hard to read. And then next, probably what we're going to have a look at is feedback topologies, advantages and disadvantages, effects on circuits, also how we can analyze and implement feedback amplifiers and their topologies. And we'll have a bit of a look too at the stability and oscillators, and then waveform generators and VCOs we're actually not going to cover as much. You had a look at these in your labs. Definitely refer to your lab manual. We can have a quick look. I might just do a little quiz on sort of like which type of Schmidt trigger is which, just for quick questions. But these waveform generators you have sort of had a fair bit of experience with in your labs, whereas we do a bit of the feedback topologies, but we'll have more of a look at those. And then analog to digital and digital to analog. There's sort of just a few different circuits to have a look at there. We probably won't be too, I guess, over the top with those ones. So before we begin, I'm going to share this drive. You might not have seen the ELSOC drive, but I'll send it into the chat because I think it's important to have access to. There's sort of older years finals in here, and they can make a big difference when you're getting into that sort of last stage of preparations. So moving on, we essentially have 4 different types of feedback topologies. So first and foremost, we have essentially they're different combinations of series and shunt. So series shunt, shunt series, series and shunt. So just as a quick test to see where we're at, can anyone tell me what the topology of this circuit is? So we have I guess input is V1. And then our output is going to be V2. V2's this voltage at this node. Any ideas? Any ideas? Series. Excellent, Leon. So how do we go about figuring that out? Did you have a process? Feel free to unmute or chuck it in the chat.
I just checked like the nodes for the feedback network and the input outputs.
Excellent. So first of all, let's put a node for our input. So we're saying input is here. Whoa. Output is up here. And then for our feedback topology, remember it's going to be where our two circuits are connected. So we've got one node here and another node here. So is the blue the same as the green on the output? Clearly they're not. So we consider that in series. And same at the input. They're not the same node, so they're series. It's as simple as that for sort of understanding. So that was a little quick quiz. If that's sounding new to you, don't worry. We're gonna look at some of the content there. So coming back to feedback topologies, there's a good stack exchange sort of whatever you'd call it thread where they're talking about describing sort of feedback topologies. And some of the steps that Aaron would have gone through, he took you through as well, that are outlined in this thread are to identify sort of the network or the element that's connecting the two. At the output side, if the feedback is connected directly to the output, it becomes voltage or current. So they use a different terminology here, but essentially voltage is shunt and current is series. And then at the input side, if it's connected directly to the input and the feedback, then it's called shunt, else it's series. And you also name it like output then input. So shunt series is output is shunt, input is series. So in terms of an intuitive way to understand this, someone described it as in sampling, we don't want to, sorry, that was really weird, don't want to affect the output, right? So if we have voltages, say I want to sample the voltages, then I would do that in parallel, right? It's the exact same as when you, say you want to check the voltage across this resistor, you connect your multimeter or your voltmeter in parallel across it. And same for currents. So in currents, we put them in series so that we can just have a look at what is happening to the current. The exact same thing with the output. If we want to sample a voltage, we do it in parallel or in shunt. If we want to sample a current, we do it in series. It's actually the opposite at the input. So at the input, what we want is for the essentially to be able to affect it, right? Because we're using feedback to feedback into our system. So we want to add a voltage. We might not draw that. We want to be able to add a voltage in series. I'm not really sure how to, let's just say this is our V source. We want to add our feedback voltage in series in order to affect what our input is. And same for currents. We want to have currents flowing into the same node. So this can be our I source, and then we have our I feedback, both feeding into the same node. So that's why any voltages that are the same, if we want to mix in voltage, we could do it in series and current becomes in parallel. So that gives us this nice table, which is series is voltage in, current out. So remember, series is essentially voltage being able to affect itself, and then current in series because we're measuring current. Series shunt means that we're measuring the voltage at the output, but also the voltage at the input. Shunt series means we're measuring if it's in parallel, we're affecting the current flowing in at the input. So we're looking at the current at the input, and then series, we're measuring the current at the output. And finally, shunt is the essentially affecting the current at the input, but measuring the current voltage at the output. So anytime you're thinking about it, at the output, we don't want to affect it. And so we measure voltages in parallel, currents in series. And at the input, we do want to affect it, so it gets flipped. Is there any questions about that? Or like the understanding there? Might be easy to have a look at some, like the actual pictures, I guess. So if we have a look here, we're sampling the voltage. So we want to take a little sample of the voltage, and so we do that in shunt at the output. But at the input, we want to use a voltage mixing. So we want to use our feedback to say, I want to change this input to my system. And so we do that in series. Otherwise, if we put this voltage in parallel, it wouldn't work, right? We wouldn't be able to use feedback at all. So same goes here. We have a series connection where we're having a look at the current flowing through now. And then we're also, so we're sampling current, and we're comparing or adding in additional current or removing current to act as a feedback network. For series, we've got at the output it's series, which means we're looking at a current, and then the input is series, so we're comparing a voltage. And shunt, looking at a voltage at the output, current at the input. Simple as that. 4 topologies. What can be a bit tricky is knowing which set of parameters to use. So once you've identified the circuit topology and the feedback network, so let's have another test actually. So this one we said was series. Now the next one, we're not going to have you put it in the chat. I'm going to get people to raise their hands when I say a topology, and see if you can get it. So this next one, feel free to take a screenshot, draw on it, whatever you need to do. What topology are we looking at here? And then after that, I'm going to hand over to Jack. Thanks so much, Jack, who's going to talk about general exam strategies, etc. Okay. Hopefully that's given you enough time to think. So, who thinks that this is a series? Raise your hands. Okay. B, series shunt. Any takers? Okay. C, shunt. Any takers? Okay, Alex, Leah. Okay, this is looking pretty popular. And finally, D, shunt series. Any takers? Just Chungshi. Oh, no, okay. So it looks like the consensus was on shunt. So let's verify. Let's say our output is green. We're taking output at this node, and we're our output of our feedback network is also this node, and at our input, oh, actually, that's not a good way to do it. A better way to do it is to mark your, let's say blue is feedback, and then green is like, I guess, sample and mix. So we're sampling at this node, mixing at this node, and then the exact same nodes are where our feedback network is. So this is in parallel, this is in parallel, shunt, shunt. Perfect. Well done, everyone. So we learned something, yes. Good job. Okay. Jack, if you're there, I might pass over to you.
Thanks, Peter. So I'm not going to take up much of your time today, guys. I just wanted to remind you that with these online exams, they're really tight, time constrained. So you need to be probably more efficient than you would be in in-person exams. And but the benefit is you can use tools that you can't use in in-person closed book exams. So the three main tools I would really encourage you to use during this exam: Excel, MATLAB, and Wolfram Alpha. So MATLAB is really, probably for some other courses, MATLAB's more important because it can deal with the imaginary numbers well. I would strongly encourage you to use MATLAB, use the units feature in MATLAB, because that's basically an error checking mechanism. If you put in the units, it'll do the conversions for you, and you'll also make sure that the answer you're getting is in the units that you expect. So I always found that useful for time constant methods. Like if you're multiplying resistance capacitance, you're getting the right result in the units that you expect. The other thing, I would encourage you to do in Excel is to go through the past papers and actually structure your response inside of Excel parametrically. So have like, a table of input parameters and then have like the steps for that. And then that way, when you get into the final exam, with some minor tweaks, you can basically plug in the parameters and get out the answer. And if you do that enough times, you're going to basically have like a solution to every exam question. So that's, I don't always follow my own advice. But if I were really trying to ace this exam, I would set up, a big Excel spreadsheet and have like, time constant method approach, like the op-amp gain approach, and just have it like, step by step in Excel. And that's going to also structure your thinking in the exam, so you're not going to get as stressed. I'm also going to send you through, it's probably included in the ELSOC link that the Google Drive link that Peter sent you, but there's a really good slideshow that Matt Davis put together a while back it's like 100 pages, and it's about exam strategy. Some of that's out of date because it's more related to in-person exams and how to use your calculators, set that up effectively. There's some really good advice in there. The final thing I would encourage you to do is like recognize the easy marks in the exam, and so that will be look at all the past papers and say where here is an easy 3-marker just for explaining something, and identify that, knock that out, get all the low-hanging fruit. And also, what are like some of the larger mark questions that actually aren't very challenging, that are sort of a bit rote. So for me, I think for this course, I found that some of the open circuit time method stuff, it's quite rote. Once you learn the method, it's quite simple to apply and it's not very error prone. So really just get used to identifying those questions that you've seen before in the exam, and have a really good method of just knocking that out. Also, I would obviously encourage you, if you have a tablet or something like that, to test that beforehand, test how everything works beforehand. But also, the benefit of having doing the questions on a tablet is, you can much more easily rub things out, and that's actually really important in the exam. Like if you're writing on paper, and you're having to scratch things out, it just adds a little bit of time and a bit of stress that you don't need. So, does anyone have any questions about what I was talking about with the Excel spreadsheet? That's something which in finance, I do finance as well, and I think that really helps in a lot of finance exams, is having a sort of pre-prepared spreadsheet where things are parametric, but it also is beneficial in a lot of engineering courses. So if anyone's got any questions about that, just let me know.
I was wondering, Jack, sort of how do you picture that, like helping with an exam, and why is that better than having, say, just your calculator ready to go?
Yeah, so the issue with having your calculator just ready to go is just an in-person, like just a calculator, is if you've got a large fraction and you're plugging in the parameters, it's really easy to lose a decimal point here and there, an order of magnitude here or there, and that's just throwing away marks, right? So you really want to be able to see it in a way. Like I always found the calculator like quite tedious. Like it's like you've got a long fraction on top of a long fraction. It's just really easy to lose track of that. So just use the fact that you're doing this exam online, and you've got access to all this stuff. And again, MATLAB's really good for imaginary numbers. It's maybe not as relevant in this course. There's aspects of it which are obviously you use imaginary numbers in every electrical engineering course to some extent, but keeping track of phase and that sort of stuff is MATLAB's really great for that. Just the inbuilt functions, and again, Wolfram Alpha, like it's just a better calculator, is the way I see it. So I would never be, I can't think of when I would be using an actual calculator in an exam like this over something like Wolfram Alpha. Like that is better in almost every instance, apart from very basic calculations. So I guess it's just using the tools that we have, and it's actually more practical as an engineer. You're going to be using Excel and a lot of very structured approaches a lot in day-to-day engineering. So you should probably also, it's good to get used to that and have this structure for solving problems, not just like this rushed exam, just get it all out there on paper in a messy way. If you set yourself up in Excel beforehand, I wish I had an example. I saw that chat question. I wish I had an example, particularly for this course, but I actually don't. So it's just I think it's probably a worthwhile thing to do is look at some of the questions and see, are there similarities? That's a great idea. So, or even like a MATLAB script or something along those lines, just something where it's parameters and you just need to make slight modifications. But that's going to come out of, going through lots of past papers and doing what you would do normally, I assume, which is identifying similarities between the questions and saying, where can I generalize? Where can I just sort of almost rote learn how to solve this problem in an exam situation? Obviously, knowing the theory behind it, you have to know the theory. But electrical engineering exams, they don't test necessarily how well you learn the theory. That you have to answer things quite quickly and precisely as well. So, I mean, if Peter has a spreadsheet developed or something like that, then I'm sure that'd help. I'm not sure. It's something where like students are kind of learning how to tackle these online exams, because they are a lot more challenging in a lot of ways. Since online exams have started, I don't think I've finished an online exam in full. They really test your speed, because they don't want you being able to look at tutorial solutions and simultaneously like just copy the tutorial solutions and substitute values. So they really are, it's a speed game, and anything that makes that faster, like a script, or you could do a Python script or something like that, an Excel script, something that's structured, visual, it'll de-stress you a lot. You'll be able to map the exam questions onto things that you already know, that you've already prepared for. And it's also a worthwhile use of your time. Like if you're doing past papers, then you may as well be doing them in some sort of way that replicates how it's going to be in the exam, which is like plugging values into Excel or plugging values into a live script in MATLAB as well. Live scripts could be really useful. That's something which I would encourage you guys to learn, particularly for some of the later courses you're going to be doing. So control systems, DSP, MATLAB live scripts are a godsend. Yeah, they're fantastic. So they're like, it's a lot of ways it's like better than LaTeX, because you can really structure things in a nice way. So I would encourage you to really get familiar with your like MATLAB as well, just in general. But it will be useful in this course as well.
Jack, I was wondering, sometimes we get questions and it seems so unfamiliar, even though it's stuff that we do know. How do you recommend tackling those things where it's, the same content but maybe brought to light in a different way?
Yeah, that's. I mean, I've always struggled with situations like that. Just the sort of exam stress. The first thing I would probably do is like dig the parameters out of the question as well. So if you this course, you won't get really wordy questions. I mean, you get that for 3105, but really dig out like what information are you given and what fundamentally are they testing, and then go back and like try and answer the question in the way that it's phrased. So relate it to the content of the course, like what part of the course is it coming from? And then if you're really struggling, you can look at notes, and sometimes there's hints in notes. Like, I mean, I think it's one of the more, that's one of the hardest questions to answer, is like, how do you answer a really unfamiliar question? Sometimes you just get stuck and you need to get open all the lectures and then Control F or something like that, and really just try and quickly refamiliarize yourself with the concepts. But hopefully 90% of the marks are things which you vaguely know and are familiar with. And again, it's a matter of looking through the past papers. Like, there's a possibility that one or two questions might be out of left field, but the more past papers you look at, the more tutorial questions you look at, the lower the likelihood of that. So I'd just be focusing on the 90% of marks, and obviously there are the 10% that are really differentiators, which you need to have in every exam. But you're gonna just deal with that. And there's an aspect of luck to that as well. Some people just, something clicks and they manage to solve those sort of left field questions.
Thanks so much. Did anyone else have any other questions? Please make the most of Jack while he's here. If not, was there anything else, Jack, that you think might help with the?
No, I'll send through in the chat the file, that big long file, the Matt Davis one, and awesome. That'll probably be a lot more helpful than what I've said. I'd say, because he's a bit of a legend. He's got so many notes and stuff like that. So I think it's this one. So that'll be pretty helpful. Obviously, the stuff about setting up your calculator is probably not as relevant given what I've said about online exams. But yeah, I just encourage you, to really have quite a systematic approach to these exams. Don't treat online exams like in-person exams, as tempting as it might be. And a lot of you would have the benefit of not having sat that many in-person exams, apart from your HSC and that sort of stuff. You have to treat these like a different. They're a different animal completely, and you really are being tested in a different way. It's a lot more about speed. Like, in-person exams, generally people finish them, but these ones, a lot of even the smartest people like Peter, he's said to me that just exams that he hasn't finished. So it's you've got to, and if you are finishing it, it's probably missed something.
Yes, don't expect to finish. I think that's great.
Don't expect to, and really prioritize your time. Figure out where can I just knock out, get an easy 15 marks for this question. That's a matter of practice as well. Identifying what's just easy marks and really getting those. Because this can be a challenging course. A lot of people find this challenging. So you've really just got to make sure you get over the line, which is scraping up the low-hanging fruit, and then then tackling the harder questions. A lot of the hardest questions are actually 4 to 6 markers, I find. Those are the ones that really separate the distinctions from the HDs. So in some ways, and again, the benefit of a tablet is you can sort of move stuff around really easily. So you can go A, B, E, and then C and D are sometimes those 4 to 6 markers. And fill them in later, because those are the ones actually which are often hardest. And they rely on A and B, and E is a completely separate part of the question, which is high marks, but it's easy. So again, use the technology to your advantage, because that's the whole point. They're making the exam more challenging because you've got this technology. So you really have to utilize it if you want to expect to get good marks. Cool.
And not getting too caught up with those really nitty-gritty analysis questions. It's about showing what you know at the end of the day. So sometimes being able to just send it on a question and just say, well,
I completely agree.
And do you think give everything a go, Jack?
Yeah, I would say so. I would definitely try and show knowledge in every question. Like, I would definitely try and get that 1 mark. Like, even if you're really, really struggling with a question, just the basic formula that shows you understand what, like, the most basic aspect of what the question's giving, and you'll get a mark for that. You get maybe 2 marks for that. Plug in the parameters, show or explain what you. I've done this in exams before. I've explained what I would do if I had time to do it. So I'm like, this is the very general procedure, and I'm sure I got 1 or 2 marks for that out of a 6 or 7 mark question. Because they recognize that you're going to run out of time and you have to prioritize. And people make mistakes in exams. Like, I've made plenty of mistakes in exams with time allocation. It's pretty horrendous mistakes before. So I would also encourage you, obviously, look at the clock and develop a very good flow for how you're going to upload the questions as well. This is where you can make a really big difference. So, they give you 20 minutes, which is obviously really generous. What I think probably the fastest way, if you have an iPad, is to have like your desktop computer set up, do it on your iPad, run on your iPad, and have OneNote synced so that it's automatically syncing up, and then export it as a PDF. That'll take probably 3 minutes for the entire question set. So if you've got 4 questions, it'll take 3 minutes to do the entire thing. Whereas if you're writing on paper, you have to scan those up, and it's easy to make an error there. And then if you are doing it on paper, what I would encourage you to do is definitely use Microsoft Lens and use the cloud sync functionality to that where when you upload it, it'll go to your OneDrive, and then you have your OneDrive open on your computer and have it ready to just drag across really quickly. So that's a matter of practice. Hopefully you guys have had a bit of experience with that and developed your own sort of flow for how the exam goes. But I think a lot of people probably spend to allocate themselves too much time for this uploading. Like, you use the free time they're giving you. I would say that, like, if you're spending any more than 5 or 6 or 7 minutes uploading, you're wasting time, and you can actually really benefit from an extra 10 minutes in an exam like this. An extra 10 minutes could be an extra 5 marks easily in an exam like this. So just really get the flow ready, and that the Excel spreadsheet is part of that. The only thing about the Excel spreadsheet is, again, you have to still show the working, but it's like you can get the answers and you can actually, pull the working off. And I mean, when I say like a spreadsheet, like an ideal version of this would also have like the written working next to it. So you've got like the parametric output and then the written working that corresponds to it. It sort of flows down like that. And it's something you could set up, and it takes some time to set up, but I think it would be worth it if you really want to ace like a course like this, or actually probably more later courses as well. This would be really useful. Like 3106, I think, would benefit from something like that, where there's these really generic questions that keep getting thrown up. Like having a really systematic approach would be very beneficial. Anyway, everyone's very different as well. It's very, like, people have their own approaches to exams. So there's only so much advice you can take from, like, everyone's a bit different, but that's kind of how I would approach an exam like this.
Thank you so much for your time, Jack.
No problem.
Really helpful. Unless anyone has any more questions, we'll let you get back to work. Perfect.
Cool. All right. See you, Peter. Good luck.
Thanks,
Good
Jack.
luck, everyone. Bye.
Cool. Okay. So hopefully that was a bit informative from someone who's been there, done that. Now let's get back and have a look at some more feedback. So I forget where we were at. So we were talking about the different how to identify the different types of feedback topologies that we've got. Next, we need to be able to put parameters onto those. So for these, I guess there are ways that you can memorize them, but I would just use something like this. I've ripped this table from this advice. Sorry, Catherine. Yeah, we moved online. I've had to go back home. So having a look at the different choices, if we've got series shunt, we're using H parameters. Series, we're using Z parameters. Shunt, there's a typo. We're using Y parameters, and shunt series, we're using G parameters. That's just to do with the different, essentially the different gains that we're looking at. So voltage by voltage is an H parameter. Current on voltage is a Z parameter. Voltage on current is Y, and so on and so on. Anytime you have sort of a current and a voltage, etc., it's going to be Y or Z. And anytime you've got both currents or both voltages, it's going to be H or G. What is T? T is I actually don't know. I assume beta, like A times beta. Or A, sorry. Let me just have a look. Yeah, you'll find that like with online resources, everyone has a different setup and different I guess parameters and ways of describing things. So you've just got to be able to read things with not a grain of salt, but with that in mind. Yeah, so they're saying that it's just the open negative of the open loop gain, I think. Yeah, I'm not sure. Essentially, all I really care about is the parameters there. The rest of it doesn't matter. So we also have a table that says the effects of the different ones. Having things like this sort of close at hand to refer to can be really helpful. So if I had a so voltage, this is shunt series. Knowing what happens to the gain, bandwidth, input, output, resistance, don't worry about these two. These are all things that you could get asked. So you might get asked like, essentially these are good things to have as like a sanity check, right? Ah, yeah, sure. Let me copy this link. So these are a bit of a sanity check. So let's say you've calculated your feedback as a shunt series. Oh, sorry, this might not be shunt. This would probably be series, wouldn't it? Yeah, be careful with these different wordings. Again, it's just one of those things where people call different things. Yeah, thank you, Guanji. That probably is what T is. Beta times A naught. I wasn't sure because they pulled out a 1 on beta. So I was thinking it might have been the gain or something. Knowing what the different topologies have as an effect. So essentially, like for some of them, we might have the open loop. So this is the with feedback is the open loop divided by like 1 plus A naught beta, right? So if you're dividing by this, then it decreases if you're, so it could do this, or it could do something like this, where you multiply by that term. And then depending on that, the bottom two in 3106. Yeah, you might see a bit of that in 3106. Yeah, they will be, Leon. Get keen. Essentially, this is just something that you need to learn or be able to refer to. I don't think it's particularly intuitive. There's what's going to happen to what. You can have a look through some of those resources that I've linked, and they might go into a bit more detail about why that's the case for these different ones. It's good enough for me just to be able to describe them. So we've had a look at our topology tests. We're happy there. Alrighty, let's have a look at this assessment. So this was, I think, an assessment that I did last year. We're going to have a look at a question. We'll see how we go for the full analysis, but it could be good. Are we feeling a bit of AC analysis? Any takers? Sure, let's get it. Okay. Wow, that was more energy than I was expecting, guys. That's good. So, woo, yes, love it, Jack, love it. So, who can tell me what so question A is asking us for the type of feedback topology. We're going to do a vote. No one type it in the chat, don't spoil it. So our output is V0 up here. Our input is way down here. It's a really weird diagram. But we're going to say that this is our input node here, right? Because it's essentially just flowing through here. So what is our feedback element? Do we think it's a shunt connection? Oh, I'll go sh. Hands up if you think it's shunt. Okay, Kenneth, Leon, Gabriel. Okay, we've got a few. Okay, next, do we think that it's series shunt? Any hands? Edwin may have just been left over. Nikki, okay. Any takers for shunt series? Okay. And any takers for series? Okay. So the majority said shunt. Let's have a look. So our feedback factor, our network is this R6. Right, it's connecting our output to our input. Our output nodes, V0, this is our input node, and then our feedback network is connected at these two nodes. Since they're both the same, it's shunt. Tick. Okay, cool. So that's question A done. As for description, this is like, you can literally just say, this is it. If you were thinking that it might have been series at the input, you can consider R1 as part of the feedback network. So I know it might seem a bit confusing here, but this is actually shunt. Cool. Okay, so DC collector currents. We're going to do a little DC analysis. This is always a bit fun. Let's see how we go. So first and foremost, this is a big cap at DC. It's going to go to an open circuit. So let's open up this cap, see what we get. We get R1. We get R1's not really going to do anything here, is it? It's opened. So I'm not going to worry about R1. We're going to have R6 coming up here, jumping over. R2 coming down to our BJT, just connected there. This is R3. This is 10 volts. We have our other BJT. And then this is R4. So when we're doing DC analysis, the best way is just KVL, really. So we can do a loop that comes down through R2, through the base, and then back up like that. Let's call that loop 1. Then we can have another loop that goes down through here, through R6, through and then back up. That's loop 2. There's another wrinkle in this that actually our Q2, so if we label these Q1 and Q2, Q2 will actually be in saturation. So because this was an assignment question, so also I think possibly they didn't actually realize that it would be in saturation, but we'd need to use a third loop. Go by choosing loop 1 and loop 2. So essentially we're looking for a current through we're looking for a current here, this collector current here, IC1, which has also got a bit of base current. And then we're looking for this current here, IC2 plus IB1. But actually, like, it doesn't matter, right? I just sort of chose them. This is assignment 3 from last year, Catherine. Does that make sense, George? Yeah, no stress. Okay, so let's do KVL around loop 1. And I actually go anti-clockwise. So I go around loop 1. Let's have a look at what we get. So we're going to go -10 plus R2. So we've got two currents. There's the collector current flowing through into Q1, and then there's also IB2, which is the base current. So let's do IB2 plus IC1 plus, and then we have this 0.7 volt drop, right? 0.7 volts. And then we've got R4, which is going to be, this current through here is our collector current 2, and it's going to be added to our base current 2. So collector plus base is emitter. So when you're doing these DC equations, if it was something easy like we looked at in the midterm crash course when it was just like a voltage divider or something, you wouldn't have to go through all of this KVL. The reason that this is chunky, right? It's like a 12-mark question. You're not going to get anything this long in your final, but it's good to see the process. And we're going to say that current then loops back up to -10, so that's equal to 0. We could plug in all our values and get sort of equation 1. So then let's do KVL around loop 2. And let me copy these questions for you. Yeah, exactly right, Jacob. So you pretty much just need to hit these currents, right? You just need to hit something that hits that and something that hits that. And you also want to include R4 and R3, right? That's why red goes through R4 and green goes through R3. It wouldn't have mattered if red went round the outside. Would it? Yeah, I don't know. I think it's a better way to do it this way. Because otherwise you've got to assume what VCE is, and you don't. Like, it's better to assume VBE, I guess. I don't really know. So that's the first page of this question, and then this is the next page. Cool. Okay, so similar diff, KVL around loop 2. So we're going to do a -10. We're going to have plus this was R5. Let me just label that one. So this is R5 into we've got IB1 plus, so this is the green one, IC2 plus this is R6 into IB1. So we've got IB1 flowing down through into our Q1. And then we're also going to add in the 0.7 volt drop, which goes from here to here. And then finally, it's going to be R3 times by IE1. Now, there are a few equations that we can use to remove some variables. So can anyone remember what relates the thank you, Oshik. Yeah. Your choice of loop is actually kind of important here. Can anyone tell me what relates the base current and the emitter current, assuming that we're in saturation? So when we're doing this analysis, we assume that we're in saturation. So it's collector. Is this true? Sure. That'll do, Kenneth. So at the emitter, we've got 1 plus beta times the base current. That's perfect. Sorry. What did I say? Did I say assume saturation? That's proper wrong. Assume forward active. My brain is going crazy. Assume forward active. So we've got an emitter is 1 plus beta IB, and also we know that our base current plus our collector current is our emitter current. So that means that essentially this is beta IB. So beta IB is the collector current. So saturation is for MOSFET. Yeah, thank you, Leon. That's where my brain was going. So what we can do is we can pretty much choose anything to replace these. But I guess the solutions we're using, we're going to try and get just in terms of IB1 and IB2. Because once we have those, then we should be able to go to our collector currents anyway and find what the biasing is. So it would be fine to go through and do this. Just as the little wrinkle though, with just these two equations, if you were to solve for these base currents, it would put Q2 into saturation, not forward active. So then we would have to actually have our third. Let's do that. So let's do KVL around 3. Minus 10 plus R5. And this is the sort of thing where like your MATLAB scripts can come in really handy, is plugging into these sorts of equations or solving them simultaneously, or Excel or something like that. Even just jotting down like R5 is equal to this, something. Just so then you can have a sort of symbolic representation rather than trying to plug in. But again, you've done this sort of analysis before. It's not pretty, but it definitely does work. So we can do -10 plus R5 into IC2 plus our biasing current 1. We're going to assume that there's 0.2 volts across this Q2 in saturation. So that's exactly the same as our 0.7 assumption. We're assuming that once it's in saturation, the voltage across the committer, the collector emitter is 0.2 volts. And then we're going to have R4 into our emitter current. So again, this is using this equation here, so this emitter current here. So essentially, a lot of these currents are fairly interchangeable. Being able to swap between them is a good skill and say, oh, okay, I've got to get rid of that. I'll replace it with this because it's in forward active. Like this is only true for forward active. Same for this one. This one's true always. Cool. Well, actually, I don't know if it is. Possibly not. Anyway, so this is our third equation. I encourage you to have a crack at solving all three of those. Essentially, let's rewrite equation 1 as 9.3 is 649.2 IB1 plus 1.2 IC2, and then equation 2 is 9.3 is 5.17 IB2 plus 0.47 IC2 plus 470 IB1, and then equation 3 is given by 9.8 is equal to 1.67 IC2 plus 1.2 IB1 plus 0.47 IB2. Okay, so we've got three unknowns, three equations. Then we can find IB1 is 3.98 microamps, IB2 is 0.929 milliamps, IC1 is equal to 0.398 milliamps, and IC2 is 5.59 milliamps. So that was a lot of work. You're never going to get a DC setup question like that, but I think being able to see the steps of loops, getting your equations, solving them for any sort of combination of IB, IC, or probably IB or IC, right? Because you're just going to replace IE with the sum of these. Finding some sort of combination of loops to get those will work, right? It might be a bit janky, but it will work. So we've got our biasing DC currents done. Any questions there? Cool. Okie doke. So now the fun stuff. We're going to start looking at the open loop amplifier, taking into account the loading effect of the feedback network. Open loop amplifier. Cool. Okay. So we're going to get rid of our R6. Just give me 2 seconds. So let's remove our R6 and we're going to take it to the input and the output. So we remember that this was a shunt-shunt connection. So for a shunt-shunt connection, let's bring it down to here. So this was part B. Let's bring it down a bit. This is part C. Cool. So to shunt-shunt network, what does that mean our feedback network looks like? We have the feedback, R6 sitting between them, and then output current, and this is our output voltage. Simple as that, right? It's a super simple feedback network. You might get something a bit more complicated. You might get resistors in shunt as well, not just this nice series one. Don't stress it, just draw it out. Definitely check out all the tutorials that you can for determining these, because they can be, I guess, tricky. Tricky to get to this stage. So this is sort of like must be able to get to this. So once you can get to this, like two-port stuff, it's pretty straightforward. The hard part is just drawing out this circuit pretty much. So let's have a look at our two-port parameters. So who knows what parameters we'd be using for shunt-shunt? So we've got that table. Can anyone remember, or shall we go back to it? Save me having to change notes. Y, thank you, Kenneth. So we've got our Y parameters. So remember, shunt-shunt is at the output, we're looking at a voltage. At the input, we're adding a current in, mixing in a current. So we're going to have a voltage and an output. It's going to be Y or Z. It's Y in this case. So if we want Y11, wow, that was not a Y. Y11 is going to be equal to I feedback, which is our feedback current coming in, divided by V feedback. Right? It's just this current on this voltage, evaluated when our output voltage, VO, is 0. So we're shorting this. Wow. I don't know if you can see that. It's a bit funky. Okay, let's just see how we go. Might have to restart OneNote. Just bear with me for a second. Can you show how to draw the feedback network as a two-port network? What do you mean by that, Catherine? As in how to know what is what? Like how do we get to this stage?
So basically, like the feedback network has an input and an output, right?
Mm-hmm.
But then that's like 2 points. But then there's like 4 points in the two-port network.
Yeah, just ground. It's just
round.
Ground. So like.
Oh, ground.
Yeah, this is just the ground point, right? Because our feedback Let me see if I've got a picture. Our voltage input, right, is between the negative and the positive. Here we're saying that our input is grounded, right? So this just goes to ground. So that means VF is grounded as well. And that's same for this current output. The majority of the time this is grounded too. Does that make sense?
Can you show another example? Like if the feedback network was a bit more complicated, what would the two-port network look like?
Yeah, let me have a look. See if I've got anything. Yeah, something like this, say. So here we've got more resistors, right?
Okay.
So we're going to say that this is our output port and it's also our node, but then this is our output and our input. So we're going to say that this here is our feedback network. And essentially the network that we're going to draw for this is just going to be like from the green X's, right? So the green X's and then ground. Does that make sense? So it's going to be RF and then down to ground is RS1 and this is RS2 and then ground.
Okay, I think that makes sense.
Yeah, so this is going to be our V output. This is going to be our feedback voltage. It is confusing. Yeah, I know what you mean. Like you see the line drawn along the bottom. It's exactly the same.
That's always ground.
More or less. It might not be. Like there might be tricky things, but I can't imagine they would show you one where it's not ground.
Okay, and also, yeah, could you just sort of explain why those three resistors are part of the feedback network?
Yeah, so this was something that I thought was a bit vaguely explained as well. I think Aaron probably has explained it in a tute somewhere. But when we're doing shunt measurements, essentially he says to trace a current from the output and see where it goes, pretty much. This current's going to go like that. And that's our feedback. I think if you want to, you could probably delve more into it, right? But it'll always be fairly, I don't want to make promises, but usually it's quite obvious what falls under that. So if you're doing a shunt mixing, sorry. If you're doing like sampling the current, then sort of apply a current and see where it goes. So this current's going to flow through here. If you're applying a voltage, then I guess see the effects of that voltage. It's a bit vague, I agree. I don't really have a good answer for you there. I'm sorry, Catherine.
Okay, that's all right. Thank you.
That's okay. Did anyone else? Yeah, it is. Sorry, Jacob. I don't really know how you tell a series at the output. You'd have to look back at your notes and tutorials and see how we do it. Yeah. I don't have any examples that are series at the output, unfortunately. Cool. Okay. Let's come back to this one. Thanks very much for your questions, though, everyone. Keep them coming for sure. Because I can 100% agree that I've probably asked these same questions and a lot of people will be wondering the same thing. So you're actually doing everyone a favor. Cool. So if we short circuit V0, essentially this is just 1 on the impedance. It's just going to be 1 on R6. Oh, this is sad. I don't know why OneNote's freaking out. I'm going to open it online. Just bear with. Usually have a bit more luck with that. How's this pace treating everyone? Can I go any faster or any slower? Okay, no worries. Thank you, Catherine. So we've got 1 on R6. Essentially, Y11 and Y22 are going to be our input and our output loading effects. So I think this question asks us to draw the open loop amplifier taking into account the loading effect. So that essentially is just asking us to find Y11 and Y22. So this is what I was talking to Jack about. It's those questions where they're worded differently. Possibly, they're not just asking you to straight like calculate Y11, calculate Y22. You need to know that, okay, loading effect is those two parameters at the input and the output, and then being able to use that. Is really important. So Y22 is again the exact same thing. It's going to be I0 on V0 when Vf is 0. Sorry, it's not very neat. Which is going to be our 1 on RF again. Sorry, R6. Cool. Okay, so then if we want to draw this without loading effect, without the feedback, essentially we just want to get rid of the feedback factor or the feedback network from our circuit, and then tack these on at the start and at the end. So I'll just do it really, I guess, badly. See if we can get a white. If this ever loads. Cool. Okay, so we're going to get rid of this, get rid of that, get rid of that, and then we're going to tack on our input and our output. This is going to be essentially 1 on Y11 and then 1 on Y22. So this is going to be R6 and this is going to be R6. And that's all that it wants us to draw there. And then having a look at the next question, it's asking us to find the beta of the network. Oh, we haven't done that yet. So beta, any ideas what might give us beta? Where would we find the feedback factor of this two-port network? Yeah, exactly right, Catherine. So Y12 or Y21. So we had a look at the input and output loading effects. Let's have a look at Y12. So using this same one, Y12 is going to be given by IF on V out when VF is 0. So we're shorting this. So if IF is going this way, but we're applying a voltage here, essentially we're saying this is V0. So when you're doing two-port stuff, I know you've covered these in 2134, but I think it's good to have another think about them. We think about whatever's on the denominator as like, that's what we're applying, and then see what happens for this one. So I'm going to apply a voltage V0. Got my R6. That means I'm going to have a current flowing around here, right? I, which is going to be V0 on R6. So then IF, which is going this way, is going to be negative V0 on R6. So IF on V0 is -1 on R6. And this is our feedback factor, beta. Cool, okay. Not too much trouble there, hopefully. Next one might be a bit more annoying. We're going to have to find the, we found the beta. Mid-band open loop voltage gain. Cool. So if we want to find a mid-band open loop voltage gain, what equivalent circuit are we going to have to draw? Any takers? Hybrid, yeah, cool. So we're going to have to do, and remember we're going to do our open loop. Let me just, so it's the mid-band open loop voltage gain. It's an open loop voltage gain, right? So we're going to have to use this circuit here. So let's convert this circuit without our R6, but with our loading effects into a equivalent circuit. Cool, so I'll draw out the whole big thing. AC analysis. We're going to want to since we have a shunt connection at the input, let's consider this IS instead. It's literally the same thing. We're going to have a source. Source resistance. R1 is going to be here. This is our loading effect. We're going to bring a shunt R6 into the mix. And then we have Q1. So Q1, we're going to have R pi 1, and then we're going to have either GM V pi, or another good way is you can actually just write this straight as beta IB1, right? Because remember that GM is I forget these equations even. You'd know what GM is. It's IC on B thermal or something like that. But you can relate GM, and for part C, we don't need to. What was part C? I don't believe so, Catherine. Possibly you do. Possibly you do if you want to find the feedback. But like, feedback should be outside of these transistors, right? Like the feedback shouldn't include the internal resistances of the transistors, if that makes sense, because we can't change those. Does that answer your question? Yeah. Good thinking, but again, just follow the process that's been laid out by tute questions and that sort of thing, and it should be okay. We have our R3, which goes to ground. And then we have R2 sits in parallel up here. We're grounding our 10 volts. It's a DC source. And then we have our next transistor. So we have R pi 2, R4 sitting on the emitter. And then beta IB2. We've got R6, our output loading effects. And then we have R5. And then we have V out. Finally. So it only took us this long. So what we're looking for, let me just get rid of this page. We've got this big long circuit, which is actually, you know, it's not so bad. I think everyone should be able to pick up marks. Oh, sorry about that. Everyone should be able to pick up marks going from this circuit to this circuit. If you can't do that, definitely go back to it, because if this is not correct, then any analysis you do after that is, you know, A, it's probably going to be really annoying because there's something wrong with the circuit, and there's not going to be any things that you've seen before because it's not the right circuit. So we're looking for the open loop gain A0, V0 on IS. So remember, it says shunt input and a shunt output. So measuring the voltage at the output, and then in shunt, we're adding in a current. So let's do the output voltage on pretty much all the variables that we have in here are IB2, IB1, V0 and IS. So to be super systematic about it, why don't we start with this this setup? So stop me if I'm wrong. Essentially, I'm working my way back from V0 to IB. I'm getting the ratio of those two. And then I'm going from there, jumping across to here. Then I'm going from there, jumping back to IS. And then I can say, well, this jump plus this jump, well, this jump times this jump times this jump takes me from V0 all the way back to IS. Simple fractions, but intuitively, it's a much more manageable chunk, I guess. So let's start with V0 on IB1, right? Well, we know that, sorry, IB2. That was really bad. V0 on IB2. I've got V0 here, and then I have a current flowing. Essentially, we can think of it as flowing up through these two resistors and then down through here. So V0 is going to be equal to V0 on R5 parallel R6 is going to be equal to that current, but it's not quite that current, right? Because here V0 is across these two resistances, so it's actually going to be a negative current flowing down through them. Then we can say that V0 on IB2 is minus beta R5 parallel R6. This was sort of our classic gain, right? Minus beta RC. Shouldn't be too much of a hassle to at least get that nice output one. The annoying ones start to show up in the middle. So we're going to leave this one for now. So let's look for IB2 on IB1. So IB2 is here. It's the current flowing through this node. I'm just going to highlight this little section. Yeah. Let's see how we go. Did that work? Don't think that worked. Okay, I'm just going to redraw it. So we have our, actually, let's just stop here, right? Essentially, you've got to go from IB2, which is here, back to somewhere that you see IB1. So we've got something in terms, a current in terms of IB1 here. So let's stop there in our circuit analysis. We don't really care what happens beyond here. We've got R2, and then we've got R4, got R pi 2, and then we also have this annoying beta R IB2. And this is IB2. So we've said that we don't care about the rest of this circuit. I want a way to be able to not care about the rest of this circuit either, right? So I want to be able to chop it off here. Does anybody have any strategies that we might be able to use to chop off our circuit there? Any ideas? So by chopping it off, what I'm saying is I want to essentially get everything onto the base side. I want to reflect some things back onto my base side. So then everything's chilling on that base side and we don't really have to worry about the rest. Let's have a look at Aaron's typical resistance. Oh, it didn't click. Yeah, exactly right, Leon. So resistance looking into the base equivalent. So if we go through this summary, I'm looking for something like this. This is where we're sitting, right? We've got a base current coming down. We've got an emitter resistance. We're not looking for a like Thevenin resistance from here. What we are looking to do, though, is to ignore this. So what we can do is actually have here they've reflected it. Yes. This first one is what we're looking for, right? So we've got our IB1 flowing through here. Apply plus that. Exactly right, Kenneth. So here we put them in series. It goes straight to ground. The rest of this circuit we do not care about. Boom. So let's draw it exactly the same as this. R pi plus RE into 1 plus beta. Does everyone understand that? I think that is where this document is going to be really fantastic. And it's awesome that Aaron set it up for you. So we're looking at the these typical reflection setups. So let me come back to it. So you might not have actually seen this sheet in action, but trust me, it is like a lifesaver, this sort of shortcut methods. So let's get rid of this circuit. I'm just going to redraw it. Got my beta IB1, R2, R pi 2, and then this just goes straight into R4 into 1 plus beta, straight to ground. Beautiful, simple circuit. And then this one, it doesn't go to ground, but we don't really care where it goes to. Can anyone give me an idea? So we've got a current flowing through R pi 2 and R4 into 1 plus beta, the reflected emitter voltage, resistance. And we also have sort of this current source pulling current through these two. Does anyone have any idea how we might be able to relate IB1 to these? It's not quite, yeah, current division. Thank you, Kenneth. I was going to say it's not quite Inmar's favourite. It's very close though. Let's use current division. So I will agree that this analysis is not like your other courses, but at the same time, it's exactly like your other courses. So we're going to do a current division. Just be careful with this. There's a negative because this current is flowing the other way. So we're going to divide minus beta IB1. With current division, we use the resistance that it's not going through, and then sum of all the rest. Cool, okay. And then we just divide that over, done. IB2 and IB1. We're 2/3 of the way there. Only one more to go. So this is probably, if you can get this step, I'm confident that you understand these small signal questions. Does that sound good? Like, I think if you can understand how to use these little tricks, then you're well on the way to acing the exam. So then our final fraction was IB1 on IS. So let's draw our little IB1 by IS. R2 in parallel. Kenneth, I'm using one of the hacky formulas. So this is essentially like R2 parallel. This is essentially like in voltage division you do R2 on R1 plus R2. In current division you do R2 parallel on divided by the parallel combo. But since the parallel combo is like go back to your current division equations. It is a sum. I'd have to like derive it all and show you again. Essentially, I'm using the shortcut that like the parallel. Oh, sorry, it stopped clicking. Yeah, don't take shortcuts if you're not comfortable with where they come from. Kenneth, I'm just as happy for you to find that current with like a little nodal thing and all that. Yeah, no, you're all good. Trust me, these things are so. It's always good to doubt. Just like sanity check yourself. Be like, is that actually what it is? Because half the time I find my fingers doing stuff that my brain doesn't really check. So IB1 on IS, let's have a look at our circuit. So we're going to go, essentially it's just going to be another nice current divider. And let's use that exact same trick, right? We want to cut off the circuit here. I'm going to see if I can copy this because that would be handy. Ah, okay, I'm going to have to wing it. I think I remember. R6. No, I don't. No, that was RS. U2. Then R1. And I'm going to draw this out just so that it's super obvious to you. Is that R3? Yeah. R3. This is beta IB1. This is IB1. What trick are we going to use to make this into a nice, easy to analyze circuit? Any takers? How about we slash through this, reflect this into the base. Done. So we can say goodbye, annoying dependent source. You're not welcome in our life anymore. And our R3 becomes R3 times 1 plus beta when it's reflected into the base. And if you had to go the other way, it's literally just divide by 1 plus beta. It's that easy. And that's all to do with just the currents. Don't need to stress too much. Just make sure you're using the right one. Double check that sheet that Aaron's given you, or we'll make a nice one. So we say goodbye. And we say, yeah, okay. I'm going to stop erasing that. It doesn't like it. Does anyone want me to stop this and have a look at like a, I guess more of a like waveform generator sort of question, or are we sort of happy with the level of detail that this is going into with these sorts of questions? Just because we've got about maybe 10 to 15 minutes left, so I'm happy to get through the rest of these or check something different out. What are we feeling? I understand these are, you know, these are quite dry, long questions, but yeah, feel free to drop in some feedback in the chat. Otherwise, I guess I'll just keep going. So this is going to be a little bit annoying, but like we're nearly there, right? So let's do we could do a we could do a current divider to find this current, and then another current divider. We could do some tricky things where we turn this into an equivalent circuit where we've got IS, RS on RS plus R1, and then we have RS plus R1 here, and then R6, and we get them all in parallel. That's probably a neat way. Don't stress about how you get here. Essentially, we've just got resistances and a few currents, and we want to find IB1. So then we can say that IB1 is this one, so R6 parallel RS plus R1 divided by R6 parallel RS plus R1 plus R pi 1 plus R3 1 plus beta times by this current, which is going to flow in and down, so we're all good for signs. IS RS on RS plus R1. Take this RS to the other side, under there, and we can write out a huge big expression and then crunch the numbers. So I'm going to consider that question done. And the main thing that we learned was this sweet reflection trick that lets us essentially break our circuit up into little sandwiches, little ratio sandwiches. Right? There's a sandwich. There's another sandwich. And here's our third sandwich. Let me put them together and eat it up. Cool. Okay. And then closed loop mid-band gain. How do we go from open to closed loop? This is mercifully simple. So I can't even remember what question this is. So I'm going to come back to this table. So we're in shunt. So we've said that our actually this is a really bad table because it's not called shunt series or whatever. I'm going to say that if it's current, that means shunt. So my gain should decrease. So what a decreasing gain means is that I'm dividing by that 1 plus A naught beta. So my closed loop, AV or AF, is going to be A naught divided by 1 plus A naught beta. A naught I got from this, beta was -1 on R6. Should be able to find our closed loop. Input and output, again going back to the effects, So we're looking at current. Sorry, it was current shunt. So decreases. The input resistance is going to decrease. And the output resistance should also decrease. Okay, we're looking at voltage shunt, sorry. That's what the shunt means. So both input and output resistance should decrease. So we're going to just do that same division. If we were finding them, we're essentially just looking for the input and output resistance to this circuit, which I'm just reloading. And I don't think we're going to have time to do the cutoff frequency stuff. Essentially, use all the tricks that you've got up your sleeves. So, as Leon said, it's 12 different equivalent resistances, but there are sneaky ways to find those resistances. And as Jack recommended, have something ready to go to crunch the numbers, or at least to store the numbers, just to help. Agreed. It's sort of the only way we can do these. So after your exam, you can rag on Thevenin all you like, but until then, it's your best friend. Just think, I love this. I love finding equivalent resistances. Change your mentality. So input with feedback is our input open loop on 1 plus beta A0. Open loop with feedback is open loop divided by 1 plus beta A0. And that's just because of due to the topology, which is shunt. Cool. Okie dokie. Unless there's, might be able to squeeze something else in. This has been a very long question. Your exam is not going to be like this one, but this has been good to see the layouts that we might see. Yeah, these are good equations. Don't forget them. These are your circuits. You should be able to draw these in your sleep, hopefully, by now. Yep, this is Miller's theorem. Again, if this is sounding new to you, definitely come back to it. A lot simpler. These are a few funky ones as well. Across this dependent, like voltage dependent current source, voltage VCCS. You can think of a resistor as a voltage controlled current source as well, right? So essentially this has the same, this is the same as a resistor. We should be able to hopefully smash out any analysis questions that we get slapped with. something like this, it's always a good idea, just choose a voltage. Is this the one that I want? Essentially being able to choose, like, just assume a voltage and then see what happens in your circuit. VL, then if this is saturating, it's either going to hit VL or minus VL. And then sort of work backwards from. Has any other questions? We might leave it there. That was, I know, very. Can you show Miller's? Work through it with your friends and see if you can get some, I guess, consistency. It's always a bit stressful when you're getting different answers to what your friends are getting. But at the end of the day, you're all probably better at this than I am at the moment, just with the, you know, having it fresh in your brains. So you're each other's best resource. And be supportive and be kind on yourself. This is not easy for anyone, and it's worthy challenge, I think. But yeah, all the best with your final. Does anyone have any last minute questions? That you get solutions for? Yeah. Have a look on the YouTube, Chung Ching. I might do a little stream running through the paper or something. Best of luck with your final.